Now, mass action law. So what is mass action law in semiconductor physics? This is very important concept. That is, mass action law says that N into P equals to Ni square. This is the main statement. So in theoretically, so what is N? N equals to the number of free electrons. That is, number of free electrons or concentration of electron in centimeter cube or meter cube, as in that is concentration between the centimeter cube or meter cube. What is N? N is the number of free electrons or concentration of electron. What is P? It's the number of holes. It's the number of holes or concentration of holes. It's denoted also in centimeter. That is electron holes or concentration of holes in centimeter cube or meter cube. Now, what is Ni? Ni is intrinsic concentration. Intrinsic concentration. So also denoted as centimeter cube or meter cube. So what is intrinsic concentration? So what is the statement of mass action law? You write the statement you write. I'm saying that in a extrinsic semiconductor under thermal equilibrium, in a extrinsic semiconductor under, that is intrinsic, both two type of semiconductor, one is intrinsic, another one is extrinsic, that is impure. If we input the impurity atoms, that becomes the extrinsic. So thermal equilibrium in a extrinsic semiconductor under thermal equilibrium. What is meant by thermal equilibrium? Thermal equilibrium means at a constant temperature or a given temperature, that is T constant, or T is always a given, so fixed temperature. That is thermal equilibrium. In an extrinsic semiconductor under thermal equilibrium, the product of electrons and holes concentration, that means the product of electrons and holes, that is N and P, is always a constant and is equals to, that is N, P is constant, and is what? The value is always equals to the square of the intrinsic semiconductor. Always equals to the square of the intrinsic semiconductor. The law is mainly used calculating the minority carrier concentration. Why this law is used? For calculating the minority carrier concentration. What is meaning by minority carrier concentration? Minority carrier concentration. Minority means which is lowest in that semiconductor. That means for n-type semiconductor, obviously the electrons is very much, or electrons concentration obviously greater than holes. So that's why here the majority carrier is what? Majority carrier is hole. A majority carrier is electrons, and the concentration is denoted as N suffix N, that is electrons concentration. And for minority, what is the minority carrier? Minority carrier here for n-type semiconductor is holes. It is denoted as P suffix N. N for n-type, and smaller n, that is suffix N for n-type. That is N of N means majority carrier of electron in n-type semiconductor is electron, and minority carrier concentration Pn. And Nn means carrier concentration, minority concentration and majority carrier concentration. So majority carrier is what? In electrons in n-type semiconductor and in p-type semiconductor. Now in p-type semiconductor, obviously here the majority carrier is always hole, obviously holes, because p-type. So the here majority carrier concentration is denoted as N in majority carrier concentration, that majority concentration that is denoted, that means whole concentration. So P for whole and small suffix p for p-type semiconductor. And for minority, what is the minority carrier concentration? Minority carrier means here electron, because in p-type electrons is less and holes are more present for p-type semiconductor. So minority carrier is electron, and the minority carrier concentration is denoted as n suffix p. So p is for p-type, and here n is for n-type, both. So 2p and 2n. So this is the main concept about mass action law and the concentration of minority carriers. So for calculating the minority carrier concentration, we use the mass action law. So this is because it's all of about mass action law. Now there are three main point or note here to how to calculate, and there are more three concepts about the mass action law. Let's discuss. So in the note, the first point is that what is say that a semiconductor has initially electrons and holes concentration of, if in a semiconductor first initially has the hole and electron concentration, that is electron concentration N1 if you suppose, and hole concentration is P1 respectively, by adding the impurity atom. Now we add some impurity atoms. So now the concentration becomes, now what is N2 and P2, that is it is electron concentration after adding the impurity atoms, and this is the whole concentration after adding the impurity atoms. Now the formula is become N1 P1 equals to N2 into P2. Obviously this is constant, obviously all time this is constant, and equals to obviously Ni whole square, that is intrinsic intrinsic concentration. Obviously this is the formula. If we add some impurity atoms, this is initial concentration, after the this is final concentration, then we multiply N1 into P1 equals to N2 into P2. And assuming, obviously here assuming that is the thermal concentration, that is T constant, that is thermal equilibrium present. So now so why now here from we get that is formula, that is N1 P1 equals to N2 into P2. Obviously this time always constant and equals to Ni square. So only this part we taken here. So this is the formula, another, that is N1 P1 into N2 P2. Now the second point of the note said that in a semiconductor, before doping and after doping, the product NP is always constant. As we here we can conclude that is after doping. What is doping? Doping means adding some impurity atoms on the semiconductor. Now after doping, and that is this is before doping, and after doping concentration are these two. So after doping and before doping, obviously all time this is constant in a semiconductor. So this is the second point you write in the theory, that is in a semiconductor, before doping and after the doping, the product of N into P, that is the product N into P, is always constant. This is the second point. Now the third point is what? Third point is said that the mass action law, about the mass action law, that is the mass action law cannot be applied to degenerate the semiconductor. Mass action law, MAL, mass action law cannot be applied to degenerate semiconductor. So for degenerate semiconductor, we never use the mass action law. So that's why this 3 point is important for the mass action law. Mainly first two, that is the constant term, and these are how this formula, and this formula is very important for the mathematical problem we solve later about this topic. So up to this is in about mass action law.